Alright, so in this video, I'm going to show you how to find the area under a curve. Alright, we're going to start off by stating that the area under the curve is pretty much, I'm trying to find the area below the curve or the graph and above the x-axis. So it's got to be between that. So if the area is above the x-axis, that is considered positive area. And if this area is below the x-axis, it is considered to be negative area. It's going to count as negative area or as like a hole per se. Alright, quick review. We're going to start off by a review of area of simple geometric shapes. We have a rectangle. To find the area of a rectangle, we have surface area, right? It is base times the height. Base times the height of the rectangle. In a circle, its surface area is equal to pi times radius squared, or diameter over 2 quantity squared. And we have a triangle. In order to find the surface area, we have the height multiplied by the base, and then divide that by 2. Right? The base and the height need to be perpendicular in order to be considered base and height. Alright, so in this first part, we are asked to find the total area between the curve and the x-axis. So that curve, I am going to highlight that in green, is this right here. If I can draw straight, right? This here, and this quarter of a circle. So it's between this and the x-axis. So that means that I have this triangle right here. That's the first one. Our next area we have is this other triangle. We also have, and I'm going to kind of repeat these colors. This rectangle for sure, right? We don't know if it's a square or not at the moment. And then last but not least, this last quarter circle. So we have a total of 4 areas that I'm going to find. Right? Here we have a triangle. The area of the triangle, right, is equal to base times the height, divide that by 2. And that is going to equal to, here's the base, from -6, -7, -8, it is a total of 2 units times 3 units. I'm going to divide that by 2. 2 times 3 is 6, divide that by 2, and that is equal to 3 units. So in here I am going to put 3 units. The next up we have this blue triangle. So I'm going to continue over here. Area of this other triangle, again, base times height divided by 2, -2, 3, 4, 5, and 6. That is 1, 2, 3, 4 units long, times the height starts at 0, ends at 6. Divide that by 2. Alright, 4 times 6 is 24. Divide that by 2 is 12. So that area is 12 units. 12 squared units, I should say. Next up, we have the area of, for sure, rectangle, possibly square. Right, a square is a special rectangle. We know that the height is 6, and the base is 1, 2, 1, 2, 3, 4. So it's 1, 2, 3, 4, 5, 6 units long. And that area actually is 36 squared units. So yes, this is a square. Next up, we have the area of the quarter circle. All right. In order to find that, we just take the area of a full circle, and we're going to divide that by 4 since we have a quarter of a circle. So that'll be pi r squared. Divide that by 4 since it is a quarter circle. Pi times the radius is 6 units long. Divide that by 4. We have 36 pi over 4, and that area is equal to 9 pi, since 36 divided by 4 is 9. Right? All we got to do is just add up these 4 areas, 12 plus 36 plus 9 pi, since all these are above the x-axis, and then we're going to subtract 3 since it is below the x-axis. So 12 plus area, the total is equal to 12 plus 36 plus 9 pi minus 3, and that equals 45 plus 9 pi, which approximates to about 73.274. And that there is our final answer. The first fundamental theorem of calculus, we are given 2 things that we know about lowercase f. We know that it is continuous on an closed interval a to b. I don't care what happens before a, and I don't care what happens before b. Right? The continuous parts needs to be literally in between a and b, both endpoints included. Anything before a and anything after b, I should say, doesn't matter. It cannot be continuous. Doesn't matter as long as it's between a and b, and that's what I care at the moment. Capital F is any function that satisfies capital F prime of x equals lowercase of f of x. Right? When we have this, then this is said to be true. The definite integral of a to b of f of x dx equals uppercase of f of b minus, in this case, capital F of a. Right. This integral notation looks very similar to the indefinite integral. The only difference is that now we have 2 numbers, real numbers, a and b, right? And that means that our interval is what we're caring about right here. This is a, it's this a, this b is coming from that b right here. Right, so what does this mean? All right, so if the integral from a to b of f of x dx, this means that I also mean that I want to find the indefinite integral of f of x dx solved from a to b. You're not going to see a lot of this notation, all right, specific this, right? What this means is that I need to find the antiderivative of lowercase f, which is uppercase f of x, solved from a to b. What that means is that I need to find f of b, subtract that to f of a. All right, so kind of leading back to the fundamental theorem of calculus, otherwise noted as FTC in some places. Right, again, these are limits. Right, think about it as start at the bottom and ending on top. Kind of a popular reference like Drake. Where did he begin? He started at the bottom, now he's up here. Right, start and finish. Let's get started with this first example. I'm trying to evaluate the definite integral. Notice definite, I should see some limits, right? The start is always the lower number. The ending is always the bigger number. There are going to be some cases where it's the other way around, right? All of that is, you can flip them and take the negative of that. I'm not going to show you that. I don't want to confuse you with this here. That'll be at later examples. All right. Definite has limits. Indefinite has no limits here whatsoever. So in order to find that, right, based on the FTC, we know that f of x equals x cubed minus 3x squared minus 3. We want to find its antiderivative, or indefinite integral, and it's going to be this right here. In order to find that, we need to add 1 to the exponent and divide that by the new exponent for this term. Same thing with the next term, minus 3x, add 1, 2 plus 1 is 3. Divide that by the new exponent, minus 3x plus our constant. All right, this is lowercase f. The antiderivative is capital F of x, which is this function right here. Right, the FTC tells us that this is going to equal to f of 3 minus capital F of negative 1. Right, this constant can be any number. Right, if I'm going to substitute this 3 in here to find f of 3, that is going to be 3 raised to the 4th power, divide that by 4, minus 3 divided by 3 will reduce each other out. So I'm just going to care about 3 raised to the 3rd power, minus 3 times 3, plus the constant. This is where we're going to use the calculator, figure all that out, and that is going to be negative 15.75 plus the constant. This is f of 3. Now we need to find f of negative 1. That is going to be negative 1 raised to the 4th power, divide that by 4, minus negative 1 cubed minus 3 times negative 1 plus constant. That's f of 3 up here. So that means that f of negative 1, after doing this in the calculator, we get that this equals, not negative 20, I'm jumping up ahead, I apologize. This equals 4.25 plus a constant. Alright, so now I'm going to find this here by substituting negative 15.75 plus c to this f of 3 and 4.25 plus c to this f of negative 1. Alright, so that is going to equal to negative 15.75 plus c minus 4.25 plus c. Again, c in this case is going to be 7, 18, any number, it doesn't matter. It's going to be the same exact number, because if this was 3, right, this is 3 over here, and it's not going to change because this constant is not multiplied with the 3 that I'm finding for f of 3, or it's not even multiplied over here with the negative 1 when I'm finding f of negative 1. So this is going to equal to negative 15.75 plus c minus 4.25 minus c. Our c's here cancel out. Negative 15.75 minus 4.25, that equals to negative 20, and that there is our answer. So what is the difference between an indefinite integral and a definite integral? The indefinite integral has no boundaries, right? No limits, or as they are also known, right? It is written as the indefinite integral of f of x dx. Right? This is just us finding the antiderivative. Its answer, or the work to this, is a function, right? So that is going to equal to capital F of x, and it will always have a plus c at the end of the function, plus a constant. For the definite integral, it's going to have a lower and an upper boundary. All right, so that means that this is the definite integral of the lower and upper boundary of a function. All right, the indefinite integrals can be broken down using addition and subtraction. What that means is that, right, if I have this here, right, this function here, we have a subtraction. This can be broken down as the definite integral from a to b of 3x dx minus same limits from a to b of 3 dx. This minus is a subtraction out here. You can also say that when we are adding, right, that this negative stays within there. When you find the antiderivative, right, then you need to find the values of our limits, and then we're going to subtract, right? That those answers, right, are always going to be a number. This is a number. This is another number. Find their difference, and again, the result is a number. One last thing that I did not write down here was that for definite integrals, you're probably finding area under the curve f of x. So we're going to use areas to understand the first fundamental theorem of calculus, FTC fundamental theorem of calculus. All right. Earlier we were asked to find the areas under those curves. Now we are asked to evaluate the definite integral from -8 all the way to 10 of f of x dx. All right. This is another property that definite integrals can follow. You can break down their limits as long as their limits at the very end kind of start at the same place and end at the same place. And this is what I mean. Earlier today, we found 4 different areas. We found this blue triangle, this blue quarter circle. We also found this blue, the area of this blue square, and this small right triangle. Right? This can also be broken down to say first triangle starts where? At -8 and ends at -6. Our starting point is -8. So the definite integral of -8 to 6, let's say that all this curve is f of x plus, it should be negative, the definite integral, this ended here, this triangle, right? But this triangle begins here, so we begin at -6. The x part ends at -2. Again, this is still f of x dx. Plus, the third area is a square, begins at -2 and ends at 4. Three areas, we need a fourth area, 1, 2, 3. This is the fourth area plus the definite integral starts at 4 and it ends at 10. Again, this is all from the same function, f of x dx. We can break it down into areas. Here's a start, here's a checkpoint. The checkpoint begins at the same number, Checkpoint 2 ends and checkpoint 3 begins at the same location. Checkpoint 3 ends at 4. The last checkpoint begins at the previous ending, and it ends at the overall end, which is the finish line at 10. Right, these three areas. This one we said that it was -3. This other area is 12. The square is 36. And this quarter circle is 9 pi. So when we add all that up, all the area between -8 and 10 of f of x dx approximates to 73.274 units squared. Box that in. Let me make that like that. Alright, now let's do a little bit more challenging. We're going to evaluate this definite integral starting at -2, ends at 4, and here's the function 5 over 2y plus 6 dy. If you're not using a calculator, make sure that these are the same variable, right? Yes, the variable can change on you, but the process is still the same, right? We are not going to integrate straight through because the 2y plus 6 is part of the denominator, so we're going to use substitution. U equals 2y plus 6, so that means that du equals 2 dy. Since we have a dy, I am solving for dy. I divide into both sides and we get this here. Once we have this substitution, then I can replace the 2y with u and this dy with du over 2. Alright, I am not writing down -2 and 4 for our limits because now we are writing this in terms of u. These two numbers may be the same, but chances are they're not the same, and I'm just going to rewrite this different I'm just going to write these symbols so that I know that I don't substitute 4 and -2 in here and keep and forget to keep everything in terms of u. This is going to remind me to bring back everything to y. So 5 and 2, I am able to factor that out. So I end up having this here. Let me write this down here because there are limits. What is the integral, the antiderivative of 1 over u? That is equal to the natural log of the absolute value of u. And that is solved between the lower limit and the upper limit. Again, this helps me put in black u in there. So 5 over 2 times the absolute value, 5 over 2 times the natural log of the absolute value of 2y plus 6, that is absolute value, and that is solved from -2 to 4. Alright, I am not going to put plus c. As we saw in an earlier example, the plus c's are going to eventually cancel each other out. That is always going to happen when we have our limits, our definite integral. We don't care about the plus c here. Alright, so now I'm going to just substitute these values in here. Two times 4 plus 6 minus ln of 2 times -2 plus 6, that is absolute value. No need to do this anymore because again I did the first minus the second one. Put this in the calculator and we get this to be about 4.865. In this example, I'm evaluating the definite integral from -4 to 1 of 2x plus 6 all raised to the 1 over 3 with respect to x. Again, I'm using substitution. U equals 2x plus 6, very similar to the previous one. Find the derivative, that is equal to 2 dx. So if I solve for dx, that is going to equal to du over 2. Now to substitute, right? I am not going to use those symbols. I'm just going to use a and b. U to the power of 1 over 3 times du over 2. So that technically becomes 1/2 times the integral of my two limits of u to the 1/3 with respect to u. In order to integrate this, I need to add 1 to the exponent and then divide by the new exponent. So that becomes 1/2 times 1/3 and 3/3. Since this is 1 plus 3 is 4. All solved between a and b. Since this is a number, right, I can factor this out over here. So 2 times 4 is 8. Divide that by 3. So we have 1 over 8/3 of u to the 4/3 power, all solved between a and b. Again, if I have a fraction over a fraction, the outer parts are my new numerator. The inside parts closest to the bigger fraction is the overall denominator. So this becomes 3/8 times 2x plus 6. I'm removing u, putting the x back in here. All solved between -4 and 1. Right, I put in the 1 here minus the smaller limits right here, substitute for x. When I do this in the calculator, that is going to approximate to 5.055. Again, this is telling me what is the area underneath of the curve of 2x plus 6 all raised to the 1/3, starting at -4 and ending at 1. Example 5, we are asked to find the area underneath the curve over the given interval. It's pretty much very similar, it's just a different way of asking the questions we've been asked so far. So we have a curve or a function, negative sine of x, and this is our interval. This is our a, and this is our b. Area under the curve, that means I'm taking the definite integral of negative sine of x dx, and then these are our limits, -5 pi over 6 and pi over 4. Since this is negative, right, I can factor out the negative, the definite integral between -5 pi over 6 to pi over 4 of sine of x dx. Right. From here, the definite or the antiderivative of sine is cosine, So this negative, I was wrong, I'm sorry. The antiderivative of sine is negative cosine. So this negative is this one right here. The antiderivative of sine is negative cosine of x, solved between negative 5 pi over 6 and pi over 4. Right, from here, right, you are able to factor out if you want to. I am not going to do it for this step. Negative cosine of pi over 4 minus the cosine of negative 5 pi over 6. Alright, put that into your calculator and you're going to get an approximation of 1.5731. In this last example, we are asked to evaluate the definite integral between negative 5 pi over 6 and negative 3 pi over 4 of the negative secant of x times the tangent of x with respect to x. So this is how it's written in most math books. I like putting these parentheses. That way you know that all of this belongs to the definite integral. I'll go even a step further in doing this here for you to see which is the angle to secant and which is the angle to tangent. Alright. A while back ago, you should have learned that you are able to find the antiderivative secant of x, tangent of x is one of the properties. If you don't remember that property, that's fine. That one is the secant of x. So if you take the derivative secant of x, the derivative, right, this one up here is the derivative. Alright, so this is what we're going to end up using for this here. So I am going to factor out to the negative. Secant of x, tangent of x. I'm just changing the parentheses and brackets, the grouping symbols, alright, because I'm just using one ink color over here. I just used it so you can see the differentiated part of it. Alright, from here, this becomes the negative secant of x, all solved between negative 5 pi over 6 to negative 3 pi over 4. Alright, so that's the negative secant of negative 3 pi over 4 minus the secant of negative 5 pi over 6. And that becomes the approximation of negative 0.2595, and I'm going to round to 3 decimal places, which becomes 0.260.